And I want to share my screen. So that's next. Okay, so welcome all to the Graduate Student Summer Seminar. What's the point of this seminar? Well, there's not usually a lot of activity in the summer when it comes to talks in our department. So usually people go to conferences or workshops in the summer, but I don't think a lot of that is going on now due to the fact that the pandemic kind of disrupted a lot of different things. So the point of the seminar, from my point of view, is to present some research level math that's actually accessible to graduate students who have not, are not necessarily finishing. They could even be beginning graduate students. But it's a tricky thing to do because often what people work on in real time is often quite complicated to explain in a 1-hour talk. So one has to select the topics carefully. And what I'm going to talk about today is something that I had to write up because it was used in a paper with my collaborators. Oops, this should go on, but it's not going on for some reason. I don't know why. Let's see. Okay, let me use the, why is this not working? Okay, 1 second. I have to see why I can't control my screen. I know what to do. I have to get out of this maybe. Nope. I can't, my slides are dead. I don't know why. Let me see if I can do something about that. Let me pause the record, okay? Okay. Okay, full screen. Okay, let's hope this works now. Okay, so my collaborators are Mike Catanzaro, who was a former student that was shared between Vladimir Cherniak, who's in the audience today, and myself. And everything I know about this topic, frankly, I know because of talking to Vladimir. He taught me this topic. So I knew nothing about it before Vladimir and I started working together. As I said, it's a sort of a tricky thing to give a research level talk about, say, phenomenon that are, that are quite complicated. And really what we're after is trying to understand continuous phenomena, but a good way to model continuous phenomena is with discrete toy models. And sometimes these toy models carry many of the features of the continuous models. So the goal of this talk is rather simple. I want to construct a probability measure, a probability rule on the space of trajectories in a continuous time Markov chain. I'll explain all of this in the talk, what these terms mean. So you don't have to worry about it. In fact, something like 97% of the talk is completely self-contained. All you need to know is something about differential equations and some linear algebra, and not much more than that. Some calculus, maybe. Okay, so I'm going to get started. By the way, you'll hear dogs in the background periodically. I have 2 dogs, and sometimes even a phone. Let me see if I can shut the phone off here. Okay, so that's the downside of working from home. Okay, so here are the definitions. I want to first of all start talking about undirected graphs. This is in the sense of graph theory or networks. And what's an undirected graph? It's a triple consisting of a set called the set of vertices, a set called the set of edges, and then a finite to one function called the attaching data, where the codomain, the range of the function, is the set of subsets of the set of vertices having exactly 2 elements. So it's a set of subsets of cardinality 2. So that's all a graph is. And usually people represent graphs by pictures. And here's a picture of a graph. So the vertices, often sometimes called nodes, are in this light pale green color. And the edges, in this case, are in this dark blue color. And the attaching data says that how the edge is attached to the nodes. Now, there's nothing in my definition that requires a pair of edges if they're connected by a pair of nodes, a pair of vertices.
I think this is good.
By one edge, you could have multiple edges connecting it, but I did not depict that in this picture. So a pair of vertices can have multiple edges, but I'm not allowing, because it's not necessary, loop edges that connect a vertex to itself. So if you know the terminology, if you don't, it doesn't matter. If you're a topologist, you might say this is a one-dimensional regular cell complex. If you don't know the terminology, just ignore what I said, okay? Okay, so I want to also talk about directed graphs. That's more like kind of closer to what we need to talk about. A directed graph is almost the same thing. A set of vertices, a set of edges called directed edges, and now the attaching data is different. You have a finite to one function. What does the finite to oneness mean? It means that the number of edges that connect a pair of vertices is finite at most, right? So you can't have infinitely many edges connecting a pair of vertices together. So anyway, what is this gamma naught of 2? It's the set of ordered distinct pairs of ordered, an ordered pair of distinct vertices. So in the previous definition, in an undirected graph, you just had an unordered pair. Now we have ordered pairs of distinct vertices. And here's a picture here's a picture of a directed graph where the edges are now have direction. Someone's talking and into their mic. So, okay. So, so this is an image of a directed graph. Any questions? No questions? Next. In the directed graph case, we can write the attaching map in the following way. Is this Sean? Somebody's talking. It's sort of distorting the lecture. Turn off your mic, somebody. if you're not speaking. Good. So in the directed graph case, the attaching map can be written as a pair of functions going from the edges to the vertices, which assigns to, in the first case, D0 assigns to a directed edge its initial vertex, its source. And likewise, D1 will be the function which assigns to a directed edge its target, it's the endpoint of the edge. And there's an obvious function from the set of ordered pairs to the set of unordered pairs, which is precisely 2 to 1. And if you compose with this function, with the directed attaching data, you get the underlying undirected graph. So this is just a formal way of saying, throw away the directions, you get the underlying undirected graph. That's all it's saying. Any questions? Okay. Given an undirected graph, we may construct its so-called double. This is terminology I think I invented, but probably it's a known, it's obviously a known construction. So this is a directed graph where you put all possible directions on every edge. There are only 2 possible directions. You create new edges, 1 for each direction. So what it is the set of vertices is the same as in the undirected graph. And the set of edges, you can think of it as the set of pairs given by order pairs given by a vertex and an edge, such that that vertex is attached to that edge in the undirected graph. And the function, the attaching map in this directed graph is sending the order pair I alpha, where I is a vertex and alpha is an edge, to ij, where j is the other vertex of that edge. So that's all it is. And here's what you're doing in a schematic picture. You take the original undirected graph and blang, you create a pair of edges every time you saw an edge before, having opposing directions on it. So, make sense? Okay, so you can associate a directed graph to an undirected graph in this way. Okay, so this is not important for later. It's really something that I'm introducing just for those of you who've had exposure to category theory. If you haven't been exposed to category theory, just ignore the next two slides, okay? So a map of undirected graphs, or a function between undirected graphs, is going to be functions on the from between the vertices and between the edges, so f0 and f1, such that it commutes with the attaching data. It's sort of the obvious condition, and then a map of directed graphs is defined similarly. So it's just sort of the obvious thing. And so this slide is just for category theorists. If we have the category of undirected graphs, let's call it G, and let G plus denote the category of directed graphs, then you have an adjoint functor pair. If you don't know what this means, just close your ears. So which assigns to a directed graph its underlying undirected graph. That's the functor from left to right. And the functor from right to left assigns to an undirected graph its double. And this is an adjoint functor pair where U is the left adjoint and D is the right adjoint. Again, just ignore this if it doesn't make sense to you. We're not going to use it really. Okay, so we now get to the definition of what we mean by a Markov chain. And what is that? So a Markov chain is like a very general sort of random walk. And I'm going to be talking about continuous time Markov chains, but what's a random walk? Well, you could think of the classic example is that think of this grid as the street map of a city, and you have a drunk on starting off at a street corner at an intersection, and the drunk moves and doesn't remember where he was in previous time, just remembers where he is now. And he can move in random directions at every intersection. So here he goes. So this is a random walk. So we're going to be talking about so-called continuous time random walks, which have an added feature in a classical sort of discrete time random walk. You wait at every vertex for a fixed amount of time, say 30 seconds, right? And then you jump to the next place. And you jump to a neighbor, right? In this case, you go across the street. Or you walk a block, right? I guess in this grid. So in a continuous time random walk, you're going to allow waiting times, which can have variable duration at every intersection. So what's a continuous time Markov chain? This is the main definition of our talk. It is a directed graph called the state diagram. And each edge of the directed graph is equipped with a continuous function from the real numbers to the non-negative real numbers called the transition rate. Okay, so every edge is labeled by a function, a non-negative continuous function called the transition rate. And what is it? How do you interpret this transition rate? Well, if the initial vertex of the edge is called I, and the terminal vertex is called J. Then the function K alpha, which is the transition rate, is to be interpreted as the instantaneous rate of change of probability in jumping from I to J along that edge. So we're taking a derivative of probability here in some sense, right? We're looking at an instantaneous rate of change of probability. Any questions about this? So we're not saying what the probability is, we're saying what the instantaneous rate of change of the probability is. But it's just a function as of now, right? So that's all it is. Okay, so every edge is labeled with a function. Okay, when the transition rates are just constant, so these are constant functions, the Markov chain is said to be time homogeneous. That's the terminology in the literature. And almost all the literature on continuous time Markov chain assumes this time homogeneity condition. There's very little literature, mathematical literature at least, that considers continuous time Markov chains where the functions are non-constant. When they're non-constant, the chain is said to be time inhomogeneous. And in fact, in this lecture, it's going to be very important to consider the inhomogeneous case. That's the more interesting case from our point of view. And my understanding is that physicists kind of are more interested in the inhomogeneous case than mathematicians are. And when you go to a textbook on the subject, you'll almost never see even the time inhomogeneous case defined. It's never even mentioned. There's just no literature on it, and I guess because there are very few results. Okay, so I don't know the reason, frankly. I'm not actually in this field, right? So I'm a topologist. Oh, by the way, you will almost never see a definition of a continuous time Markov chain in the way I've written it. They never draw graphs in the textbooks. Okay, so I have to introduce two conditions which are bounds on my continuous time Markov chains that are only necessary if the state diagram is an infinite graph, right? If it's a finite graph, I don't have to assume these conditions, they're automatic. So a Markov chain, which is given by a directed graph and the rates, that's that K bullet, satisfies the rate bound if for each time t greater than 0, there's a constant r, possibly depending on t, such that the rates are bounded by r when you evaluate them between 0 and t. And this has to work for every edge of the, this bound r has to work for every edge, right? So if there are only finitely many edges to worry about, that would be a finite graph. This is automatic by continuity, if you will, well, you know, every continuous function on a compact interval has an upper bound, right? So that would follow in that case. But in the infinite graph case, we have to assume this rate bound condition. And there's one more bound condition, which is not very onerous, I think, which is what I call the degree bound condition. And all our graphs will satisfy both the rate bound and the degree bound. Let degree be the function which assigns to a vertex of the directed graph its degree, namely the number of edges which actually meet that vertex. Actually, I can get away with less. I can just look at the number of vertices for which that vertex is a target. But let's just look at all the edges at that vertex. And we know there are only finitely many because of the finite to oneness condition on the degree function. So, or I want to assume that if it doesn't follow, right? So I want to assume it's finite. Anyway, so I need to know that the Markov chain satisfies that the degree has a global bound. The degree function has a global bound. There's a number d such that the degree is always less than or equal to d for every vertex. Okay. Okay, so those are the main, those are the only bounds I need to assume. As I said, if gamma naught is finite, it automatically satisfies the rate and degree bounds. Okay, so that's it. Okay, so now I'm ready to talk about Markovian dynamics. So usually physicists are the ones that write down the dynamical equations governing a Markov chain. You see in math textbooks, it sometimes appears, but it's less so. I mean, I've looked at many textbooks by now, just trying to understand what they're doing. So the main way we study this is as follows. We write down a dynamical equation. So what is this equation? So suppose I have a pair of distinct, or an ordered pair of distinct vertices in my graph, my directed graph. Then I can look at all the edges which start at I and which terminate at J and take the sum of all the rates that, so take the rate of every such edge and add them all together. So that gives me a sum of rates that connect the vertex I to the vertex J. Okay, let's call that Hij. Then I can form a time-dependent matrix, a matrix that depends upon time because these functions K alpha are functions of time. Hij will be, the matrix entry of Hij will be this Hij if I is not equal to J. And if I equals J, I just take this following summation, and the summation is introduced to get the columns of my matrix to add each column, the entries in each column should add to 0, right? That's how this is defined. It's sort of, you don't have to remember this summation term. It's just defined. It's the sum of the, if you like, these rates of edges that come into the vertex I, that come into the vertex I. And then I put a minus sign in front of it. And the idea is that this should be like a conservation law for probability. That is, if at a given vertex, you could look at all the probabilities of jumping. Well, we don't have probability, we have derivatives. So if a probability, you're going to jump, right? With probability 1 at some point, right? Or you're going to stay still, right? In fact, at any time, you're going to either stay still or jump. So that adds to 1. So if I take the derivatives, the sums of the derivatives has to add to 0. So that's why you arrange that the columns add to 0. Each column, every column, the sum of entries in every column adds to 0. So this is called the master operator. And the master equation is a matrix differential equation. P prime of t is equal to h times p of t, where P of t is a one parameter family of distributions, that is real valued functions on the set of vertices of my directed graph, right? So, and h acts on the set of functions on the vertices because h is a matrix, remember, indexed by the entries ij, where I and j vary throughout the set of vertices. So h is acting on functions on the vertices. Okay, so this is our main equation. It's a dynamical equation. We want to solve it. And here is a special case, an example, diffusion, or I should call it combinatorial diffusion. Suppose gamma, my graph, is the double of an undirected graph, and the transition rates are constant with value 1, right? So that is, every edge has a label of a rate of 1. Then H can be written as minus nabla, where nabla is the so-called graph Laplacian. This is a very studied operator in graph theory. What is it? It is the function, so the matrix entries of the graph Laplacian give you the degree of your vertex, that is the number of edges at that vertex, if I equals j, and it's equal to the negative of the number of edges between connecting I to j if I is not equal to j. in this case, the master equation could be called is known as the discrete or combinatorial heat equation or the diffusion equation. Vladimir, by the way, if I've said anything wrong, please correct me. I mean, I'm subject to making mistakes. Okay.
Okay.
Okay. Thank you.
My pleasure.
So far, so good, right?
Yes.
Okay. So the master equation is also known as the forward Kolmogorov equation. This Kolmogorov basically invented the subject. This actually harkens back to my category theory thing, but you don't even need to know it. If you have a directed graph, you can throw in, and if you have, for each edge, no opposing edge, you can sort of glue in extra edges, and you can embed your given directed graph inside a double, namely the double of the underlying undirected graph of your graph. So you're just introducing more edges. And so then you could just extend the rates on your directed graph by 0 when you have, every time you introduce a directed edge. And that yields a Markov chain on the double where some of the rates are possibly 0. And it turns out the dynamics don't change at all if you do that. They stay exactly the same, because if you have a rate that's 0, that's not going to affect the solutions of your differential equation. We're going to talk about the solutions in a moment. Okay, so the other thing I want to talk about in all of this are trajectories. But before I do that, let me just point out is that because of what I just said, we could always assume our directed graph is actually arising as a double of something. Okay, so what's a path in a graph? A path of length n consists of a sequence of contiguous edges, that is, edges having the property that the target of one edge is the source of the next edge. So we're going to let, here's some notation, let I sub k of a path be the kth vertex of the path. So I've depicted for you a path in my graph. I've labeled the vertices with this notation I just introduced by ik. So you have I1, I2, I3, I4, and I5. The path is written in red, and the edges are alpha 1, alpha 2, alpha 3, alpha 4. So that's an example of a path in a graph. Notice that the path must follow the directions of the edges. Okay, what's a trajectory? A trajectory is a path with times on it. So a trajectory of length n and duration t greater than 0, that's a time, is a pair such that alpha is a path, alpha bullet is a path of length n, and t1 through tn is a sequence of real numbers satisfying the following conditions. It's a monotone sequence of real numbers, one for every edge that appears. But it's and we're going to let t the gamma nt be the set of trajectories of length n and duration t. So here's a picture of a trajectory. Here we go. So I have the path in my previous picture, and I've just labeled the initial vertex of each edge, alpha 1, alpha 2, alpha 3, and alpha 4, by these times, T1, T2, T3, T4. I don't have a T5. And what is T1? T1 represents the jump time, the time of jumping from the vertex I1 to the vertex I2. T2 represents the jump time of jumping along alpha 2 to vertex I3, and so on. So in what follows, it'll be convenient to introduce some additional numbers, T0, which will be 0, and Tn plus 1, which is T. And so it's convenient notation. And here is some remark. The number T sub k is called the jump time at the vertex I sub k, and the number W sub k, which is the difference, tk minus tk minus 1 is called the waiting time at the vertex. So we're never going to use the waiting time. We're only going to be using the jump time in this talk. Okay, any questions? Am I going too fast? Okay, good. All right, so now, what do I have here? I want to introduce another rate, which is called the escape rate at a vertex, which is, if you will, the rate of change of probability in jumping at that vertex. So suppose I have an interval AB. What can I do? I can look at, if I'm at a vertex I can look at all the edges that terminate in my vertex I, and then I can take the rate of that edge, and I can integrate from A to B. And then I can sum up over all those edges that terminate in I, and I can take the negative of that, and then I can take e to the power of that. And that's called the escape rate at the vertex I. And I've somehow lost my ability to, what happened? I've lost my ability to use I have to somehow, hold on a second, let me pause the recording because I've lost the ability to use my mouse, and I'm not my mouse, but my pointer. Okay, so another way to say the escape rate, it's more compact form, is you take, what is happening? I don't understand this at all. Oh, here we go. No, it's not working. What is going on here?